we start, maybe before we start, just to say, so we got this announcement of the gun phishing meeting, right? In the global Poisson mail, the last one. And I think it's written that it starts tomorrow, but in fact, in most of our coordinate systems, it starts today. So it starts in the US afternoon, or and I think so. It starts some hours after our meeting, our session here. So just for you to know, right? They are in the mail. You find the Zoom link. The organizers were a little bit uncertain about the quality of their Zoom, but that, I guess, those of us who are interested will have to figure out whether it works or not. But just to tell you that gun phishing actually, I think, starts today with some of the talks. All right, it's probably time to start. So it's a great pleasure to have today Milen Yakimov, who is going to speak on Poisson geometry of big quantum supergroups at roots of unity. So Milen, I give you the floor.
Thank you so much, Anton. I want to start by thanking the organizers. It's a big honor for me to present this work here. Thank you so much for the opportunity to present it. And I was just talking to Anton. It looks like that it's the 2nd anniversary since the organizers were running the global Poisson webinar. So I wanted to congratulate them on their wonderful success and happy 2nd birthday. So I'm sure this will be running for many years, and soon we'll be celebrating 10, 20th birthdays of this series.
Okay, thank you, Milen. I don't know, 20th birthday sounds ambitious, but thank you on behalf of the organizers.
So I want to report on joint work with Nicolas Andruskiewitsch and Angiono, who are from the University of Cordoba. And I wanted to start by saying very quickly exactly what I want to present today. So in the early 1990s, the Concini, Kac and Procesi wrote a very influential series of papers in which they developed the theory of big quantum groups at roots of unity. And they studied their irreducible representations. They all have to be finite dimensional. And they created this beautiful Poisson geometric framework for studying their irreducible representations, where the important Poisson geometric notion, construction that's on the background is the construction of Poisson orders. In this talk, I want to describe a generalization of this to quantum supergroups. And there are a number of difficulties, and I will talk about this exactly where the difficulties are and how we overcome those. But before that, I wanted to start by saying a few things about these big quantum groups at roots of unity. So first of all, the data, the starting data is a complex simple Lie algebra G. Epsilon is a primitive nth root of unity with some mild assumptions that it has to be, the order has to be odd and co-prime to 3 in the G2 case. The big quantum group at roots of unity is a Hopf algebra. It has the same Chevalier generators like the usual quantum group, but the relations are the usual relations for the big quantum group, where Q is replaced by this root of unity epsilon. For instance, if we're in the situation of the big quantum group of type A1, the relations are the usual relations that are on the bottom of this slide. In the super case, we want to start with a contragradient finite dimensional Lie superalgebra G. The classification of simple finite dimensional Lie superalgebras was done by Katz. So in Katz's classification, these are the Lie superalgebras of type SL, OSP, D-type, F-type, and G-type. So what we are throwing out here are the strange ones, the P and Qs, together with the Cartan types. And from a different perspective, these are precisely the finite dimensional simple Lie superalgebras that admit an invariant bilinear form that's even. So for each of those, one can construct a big quantum supergroup, U epsilon of G. And we want to study the irreducible representations of this big quantum supergroup. And more precisely, we want to create a Poisson framework for studying these irreducible representations. Now, where is the difficulty here? In the work of the Concini, Kac and Procesi, they rely a lot on concrete arguments with computations of Poisson brackets and reductions to low-rank cases. And the key point here is that there are actually three kinds of quantum Serre relations in the usual situation. The two are written here, and of course, they are the Serre relations that are odd EI of EJ equal to 0 when the vertices are not connected in the Dynkin graph. So we want to completely do everything without doing any kind of computations with Poisson brackets and any kind of relations to low-rank cases. And the point of that is that if we are working in the super case, there are actually, even for just this contragradient finite dimensional superalgebras, there are 13 kinds of additional Serre relations, and there are up to 4 generators. So if we were simply to repeat the work of the Concini, Kac, Procesi, that wouldn't quite work, because first we'll be checking tons of Poisson brackets, and second, this won't be really reduction down to rank 2 case, but it will be reduction down to rank 2, 3, and 4 cases. So that's really a tremendous work to be done in order to check such things case by case. So in case where instead of this, we're using a completely different approach that actually reproves completely the results of the Concini, Kac, Procesi without any computations, just by general intrinsic arguments. And these arguments are based on the theory of Yetter-Drinfeld modules, Nichols algebras, and pairings between integral forms of Hopf algebras. And I'm going to present a brief intuitive introduction to this notion, so it doesn't look like we're using this technology without even explaining it. But here I want to say that we're actually going to be working with an axiomatically defined class of Hopf algebras, which is very natural in this framework. And this axiomatic class of algebras contains a special subfamilies, all the Concini, Kac, Procesi big quantum groups, the big quantum supergroups that appear on the top of the slide. And in addition, as an added bonus, we also have root of unity quantizations of 2 very interesting finite dimensional simple Lie algebras that are in characteristic 2 and 3. They're Lie algebras that were introduced by Katz, Weisfeiler, and Brown. And I will say more about this family of algebras. So next, I want to say more about the work of the Concini, Kac, and Procesi. So once they introduced the big quantum group U epsilon of G, they introduce a special central subalgebra that is generated by the end powers of the root vectors together with the Chevalier generators K. Important easy fact here is that the big quantum group is finitely generated and free module over this central subalgebra. A warning, the full center of the quantum group, of course, is bigger because it contains the Casimirs on top of these central elements. And there are a number of interesting features of the big quantum group that make it very attractive. For instance, the small quantum group of Lustig is nothing but a central quotient of the big quantum group, where we quotient by the centrally generated ideal generated by the end powers of the root vectors together with the Chevalier generator -1. And even more geometrically, now we have a bundle of algebras over the maximal spectrum of this central subalgebra. So here's the central subalgebra. If we look at its maximal spectrum, we have a bundle of finite dimensional algebras that correspond to all possible central quotients of the big quantum group, where M is a maximal ideal of this algebra Z epsilon of G. So in other words, the Lustig small quantum group is just one special fiber, but we have this bundle of algebras. And the advantage of this big quantum group is that it allows to study the representation theory of all of these algebras simultaneously. Now, the way this was approached is an old story. So it's a general picture that was developed in the 60s, 70s, and some of it continued into 80s in works of Procesi, Artin, Kaplansky, and Posner. So here A is a finitely generated complex algebra, which is modulo finite over the central over a central subalgebra Z. So in other words, it's finitely generated module over the central subalgebra Z. And now we want to understand all irreducible representations of the algebra A. And by a general result that follows from the works of these people, all of these representations actually must be finite dimensional. Oops. Now, by Schur's lemma, we have a canonical map from the irreducible representations to the maximal spectrum of the central subalgebra, which is nothing but the central character of the representation. And given a representation V, we can consider the corresponding annihilation ideal of V within that central subalgebra Z. Now, this gives us this geometric picture of this fibration. So the irreducible representations can be thought as a variety that sits on top of the maximum spectrum of Z. And the fibers for this fibration are precisely all irreducible representations with the same annihilation ideal or with the same central character. Now, if we think about this in a different way, these are nothing but the irreducible representations of these central quotients, like the ones that appeared on the previous slide. So in other words, for every point M in the maximal spectrum of Z, we have this finite dimensional algebra A mod MA, and we're looking at the fibers of this fibration, which are precisely the irreducible representations of this algebra. Now, looking back at the big quantum group, we had actually a more special situation, and that special situation was that A was actually a free Z module. And in that particular situation, we actually have a bundle of algebras where each fiber of this bundle is that central quotient that appears here and on the previous slide. So in general, of course, if we don't have that freeness, we will have more like a sheaf of algebras, and we will be studying the corresponding irreducible representations. In this particular situation, it's even easier. It's just a vector bundle of algebras. Now, next I want to introduce this very important Poisson geometric notion that was developed by the Concini, Kac and Procesi, and then later it was axiomatized by Brown and Gordon. So we're looking at a complex algebra A, and we assume that we have a central subalgebra Z. And we also assume that A is a finitely generated module over the central subalgebra Z. Now we will call this pair a Poisson order if first the central subalgebra is a Poisson algebra, so it has a Poisson bracket. But secondly, we have a linear map from the central subalgebra to the derivations of the non-commutative algebra with the property that partial Z for each element in the central subalgebra extends the corresponding Hamiltonian derivation, which is the Poisson bracket with Z on the Poisson algebra Z. So it's obvious that this is a way to somehow bridge the Poisson side and the quantum side. because in one way, we're linking Hamiltonian derivations to derivations of our algebra. So in other words, we are connecting the Poisson and the quantum pictures on the level of derivations, but it is not a priori clear that this has actually substantial applications to representation theory. And this was the big theorem of the Concini, Kac and Procesi that was later axiomatized by Brown and Gordon. They proved it in the concrete situation of big quantum groups, and Brown and Gordon axiomatized it later. So if we're looking at any of these Poisson orders, and we pick up 2 points, M and M prime, in the maximum spectrum of the central subalgebra, if they happen to be in the same symplectic leaf, then the corresponding fiber algebras are actually isomorphic to each other. So in other words, not only we have a dimension preserving bijection between the corresponding irreducible representations, but actually as algebras, they are honestly isomorphic to each other. So it's a lot stronger fact than understanding that the fibers are essentially the same. So now the upshot now of this construction compared to the classical picture from the 60s and 70s is that if we're in the situation of Poisson orders, on the bottom we have a Poisson variety and the fibers of the corresponding irreducible representations are exactly the same along symplectic leaves. Very often we also have a group acting on our algebra by automorphisms that preserves the central subalgebra. So in other words, we would get invariance of fibers not only along symplectic leaves, but also along group orbits of symplectic leaves. So this would essentially break down the hugely infinite problem of computing these irreducible representations to much more manageable problem, because we would be looking for only one point in the maximum spectrum in each group orbit of symplectic leaves. So this would drastically reduce the problem, the complexity of the problem that we are solving, the problem about classifying these irreducible representations. Where do Poisson orders come from? So there is one very easy way of getting Poisson orders, and that's specialization. And classically, we always look at specialization where we take a non-commutative algebra and we look at the specialization of this algebra that is a commutative algebra, but that construction in order to get a Poisson structure on the commutative algebra from the quantization. But this construction actually has a very easy generalization that produces Poisson orders. So here we're looking at an arbitrary non-commutative algebra, central element H in the algebra that's not a zero divisor, and we're looking at the corresponding central quotient. And the pair of A and its center actually has a canonical structure of Poisson order in the situation when I know that A is finitely generated over its center. So that was the only property that doesn't follow right away from specialization. And everything else follows trivially from specialization. If I pick up any linear section for the corresponding quotient map, so this is the quotient map, and I pick any linear function section, not algebra section, of course, such in general will never exist, any linear section, then the Poisson structure on the center is nothing but take the images under that section, commute them, that should be automatically divisible by H, divided by H, and project. Similar thing for the corresponding derivation that was supposed to extend the Hamiltonian derivations. We take a pre-image of any element A in the algebra, we commute it with the section applied to that Z. So this has to be a Z here in the iota. We commute that, divide by H, should be automatically divisible by H, and again project. And it's a very easy theorem that this is actually a Poisson order structure. In our applications, of course, H will always be Q minus epsilon for some root of unity epsilon. But one warning here. Usually the full center is going to be very singular, and doing Poisson geometry in that singular setting is possible, but it's not the most desirable thing that can be done. So the second observation of the Concini Kac Procesi is that it's a lot easier if we're actually working with a smooth subalgebra. So they were thinking like we should definitely find a large smooth Poisson subalgebra, large in the sense that it should be of the same dimension, like that central subalgebra, the full center, that turns into a Poisson order. But in order for this pair to become Poisson order, the only thing that we should really know here is that this Z is actually a Poisson subalgebra, just not any subalgebra, but Poisson subalgebra. Then automatically we can use the same map partial, and everything else will work in exactly the same way, but we have to have that large, smooth Poisson subalgebra in order to push everything further. So now to summarize, the ingredients of the work of the Concini Kac Procesi are the following. First, every quantum group is obtained, big quantum group at roots of unity is obtained by specialization, so automatically that quantum group with respect to its full center is a Poisson order. Secondly, we had that special central subalgebra that is something like a polynomial algebra generated by the root, the nth powers of the root vectors, plus those plus minus n powers of the Cartan or Chevalier generators Ki. That is actually a Poisson subalgebra. And thirdly, if I look at this Poisson subalgebra, we can actually describe explicitly what it is. And it is actually isomorphic to the coordinate ring of the dual Poisson algebraic group of a simple algebraic group with the standard Poisson structure. So if we take a simple algebraic group with the standard Skleanin Poisson structure, and we look at its dual Poisson algebraic group, the coordinate ring is precisely Z epsilon of G. And one immediate outcome of that is an invariance of these central quotients or isomorphisms of those central quotients along conjugacy classes of that simple group G.
Milen, here I'm a little bit confused, right? You know, when you say conjugacy classes of G, this means you identify the dual G itself. Right?
Precisely. Thank you, Anton. So this will come up later more and more in the talk, but we identified this dual Poisson algebraic group with a Zariski open subset of G, or with a covering of that Zariski open subset.
Right, but without that remark, right, what you're saying about conjugacy classes is kind of right. You need this identification if you want to think about those conjugacy classes.
Absolutely agree. Exactly. Yeah. Yeah. I will talk more about that towards the end when I talk about the super case, and that's precisely true. We need to have that identification. Otherwise, these are things that look like Borel subgroups. So they don't really have conjugacy classes themselves in terms of conjugacy classes of G. Right. So this was all that I wanted to say about the work of the Concini, Kac and Procesi and the Poisson geometric framework for studying representations of these non-commutative algebras that are modulo finite over central subalgebras. And now I want to say a little more about this Hopf theoretic framework that we'll be using to push this super case situation. So everything started in the late 90s with a sequence of works of Andruskiewitsch and Schneider, where they initiated a program for classifying pointed Hopf algebras. And I wouldn't really talk much about the Hopf theoretic nature of pointed Hopf algebras because they will not be relevant for this talk. But I want to provide an intuitive introduction to the underlying notions that we'll be using in this talk. Now, in that program, there is a very large family of infinite dimensional Hopf algebras. These were actually the results of the classification. They're completely intrinsically defined in terms of Hopf theoretic data. But the point for us is that they contain us very special cases, the Concini, Kac, Procesi big quantum groups at roots of unity, the big quantum contragradient supergroups at roots of unity, which we want to study. And finally, they also contain exceptional families that can be viewed as roots of unity quantizations of finite dimensional simple Lie algebras in prime characteristic, in characteristic 2 and 3. The actual quantum groups are in characteristic 0 with roots of unity, but in some way they have precisely the root systems of these other algebras in characteristic 2 and 3. And the Concini, Kac, Procesi results relied on these concrete calculations of Poisson brackets and reductions to rank 2 cases. And the thing that I want to present is using this Hopf theoretic background together with perfect pairings that would eventually avoid any kind of calculations of Poisson brackets, and we will reprove the Concini, Kac, Procesi without those calculations. So whatever pointed Hopf algebra is, it can be viewed as a deformation of a semi-direct product of 2 kinds of algebras. And I want to say more about these 2 kinds of algebras. So first, on the right side, we have the group algebra of a group G. So that's all very easy. On the left side is the notions that I want to explain. And I assume that there is, I don't assume any background in this, so I'm going to explain every single bit here. The B is a Yetter-Drinfeld module for G, and I will say like exactly what it means. And the B of V is the Nichols algebra of this Yetter-Drinfeld module. And I just want to say that to start here with some advertisement of Nichols algebra. So Nichols algebras are somehow universal tool to control quantum Serre relations without even knowing what the quantum Serre relations are. So this would be one of our strongest tools, that we would be working with these Nichols algebras that completely encode quantum Serre relations, but we will simply not care about those quantum Serre relations are because the Nichols algebras will be defined purely intrinsically. Now, the best case that's understood is the case when the group G is abelian. And I will use that case anyway in this talk only. So I want to say what is first a Yetter-Drinfeld module for this concrete situation for an abelian group G. And it is something super easy. A Yetter-Drinfeld module for an abelian group G is nothing but a G-graded G module. So this is a direct sum over the elements of G, where each of these vector spaces is a G module on its own. And we say that V is of diagonal type if G acts by characters on each of these modules. So in other words, it acts diagonally. So this is a Yetter-Drinfeld module. Let's have one example. If G is the free abelian group on n generators, and we call those generators alpha 1 through alpha n, and we keep in mind here that alpha 1 through alpha n will be precisely the simple roots of some super algebra later, then the coordinate, then the group algebra of this free abelian group is nothing but the Laurent polynomial rings in n generators. And now if we take any square matrix of size n times n with entries in C star, non-zero complex entries, this immediately defines a Yetter-Drinfeld module of diagonal type, which has a basis E1 through En, and this E1 through En will be precisely the generators, the Chevalley generators of our quantum supergroup, where the Ki, or this is identified with alpha I, the generator of our free abelian group, acts on EJ by simply the scalar Qij. And the corresponding graded subspace that corresponds to the Jth generator of our abelian group here is just the one-dimensional vector space that's spanned by EJ. Now, this is a very general setting, and there's tons of things that fit in this setting. If Cij is any Cartan matrix, you could even use a Kac-Moody algebra here, and Di are the symmetrizing positive integers. You can take Qij to be the power of epsilon, where epsilon is an nth root of unity with this power. And this is going to recover eventually, after we develop a little more, the big quantum group that corresponds to this Lie algebra G. It will be simply recovered from this setting with Yetter-Drinfeld modules. We can also look at the corresponding SLM case and write down the Qij's to be given by these formulas. And eventually, when we run the whole machinery, that will produce the big quantum supergroup of special linear type SLMN. So these are the examples of the Yetter-Drinfeld modules that we want to have. And next, I want to tell you what is the Nichols algebra, which is somehow the punchline that will be working with these algebras without really knowing explicitly their quantum Serre relations. So first, if I have this kind of square matrix, I can define a braided vector space where the braiding acting on EI EJ is the Qij EJ tensor EI. So in other words, this is what is called braiding of diagonal type. And for those of you who have not seen braiding before, I want to explain in very simple terms what exactly is the use of the braiding. So I want to look now at the tensor algebra of this vector space. And I want to think that it's a Hopf algebra in some slightly generalized sense, in the sense that it's a Hopf algebra in the category of braided vector spaces. So this has exactly the same axioms like usual, with a tiny difference that the coproduct, the usual coproduct, that the delta of EI should be EI tensor 1 plus 1 tensor EI, must be a homomorphism of algebras. But when we define the product structure on the right-hand side, we use this braiding. And we use it in the most trivial way. If I take this tensor product and I want to multiply it with this tensor product, when I move the EJ, in order to be able to multiply it with the EL, I have to pass over the EK. That passing produces precisely this scalar QJK. And this is where exactly this braiding comes into place. And then everything else multiplies in the usual fashion.
Milen?
Yeah?
Just a small question, right? So on the right-hand side of the last displayed formula, the products EI, EK, and EJ, EL. So these are the products in the tensor algebra, right?
Precisely.
Yeah,
Precisely.
yeah. So, of course, it's good that you write them without tensor. But in principle, they are products in the tensor algebra, and under different circumstances, you would have written also EI tensor EK, EJ tensor EL, right? Precisely.
Thank you, Anton. So the point here is, so we can think of the tensor algebra TV as the free algebra on the EIs. And this will be precisely the product in that free algebra. And precisely, Anton, you're totally correct that technically speaking, we should try the tensor products, which would make the formula much more complicated and harder to somehow to digest because of the extra tensor product and product, in order to keep the tensor product just for this extra tensor product. Precisely. Thank you, Anton. That's precisely what is going on. And I was sort of trying to hide that in order not to display 3 tensor products in the right-hand side. Now, what is the Nichols algebra? So there is a very easy theorem that there is a unique maximal Hopf ideal that sits in degrees 2 and higher, for which the corresponding quotient will be still a Hopf algebra in this sense. And that quotient is called the Nichols algebra of this Yetter-Drinfeld module V. And it's all very easy to say here, but somehow to continue the advertisement, eventually, if I do everything for the previous examples, this will be this Nichols algebras will be precisely the positive parts of some small quantum groups. And all of those Serre relations will be hidden in this maximal ideal. And we'll be working with those positive parts without really knowing what are those quantum Serre relations. So let's make this precise what I said. If I run everything in the case of example 1, we get precisely the positive part of the Lustig small quantum group that corresponds to the simple Lie algebra G. If we run everything for that braiding matrix that we got in example 2 on the previous slide, this braiding matrix in example 2, we just run this whole procedure, we're getting the positive part of the Lustig small quantum group of the supertype SLMN.
So how is it, those maximal Hopf ideals in those examples, are they still manageable, or they are kind of horrible, or I mean,
they are manageable. I will say later, like,
okay,
I will say later, there is a paper that actually classified completely the quantum Serre relations. So there is a paper that wrote down explicitly those quantum Serre relations. Now, there is a lot of Lie theory that has been developed in this setting, and the person who was largely responsible for this is István Heckenberger. So he, first of all, classified explicitly all Nichols algebras for which all braided vector space is BV, or Yetter-Drinfeld modules, for which the corresponding Nichols algebra is finite dimensional. And there is a beautiful generalization of the usual Cartan killing type situation, where we have, first of all, a root system that's associated to each of them. And in the super case, this generalizes the root system of the super case. Inside, we have Cartan roots, and these are the analogs of the even roots in the super case. And furthermore, Heckenberger also introduced a generalization of the usual vowel group action on root systems, but now this becomes a vowel groupoid action. And the easiest thing to think about this in relation to classical stuff that you've seen before is if you look at the super SLMN that has different Borel subalgebras and different presentations in terms of different choices of simple roots. So in the most straightforward one, you have only one odd root, but there are a number of different presentations when you have multiple odd roots. And it is a result of Vera Serganova that you have actually isomorphism between the corresponding algebras. And this is precisely what Heckenberger's theory generalizes. He establishes that not only we have Lustig braid group action on each of them, but we also have this isomorphism between the different realizations. And altogether, this is packaged into an action of a braid groupoid that was introduced by Heckenberger. And what we're acting on is on the Drinfeld double of these semi-direct products that appeared before. The semi-direct products in themselves are like versions of the Borel subalgebras, and the Drinfeld doubles are versions of the quantum groups. Of course, we duplicate the Cartan generators Ki, but we don't care about that. So these are now vast generalizations of small quantum groups, and they appear very naturally in this setting of pointed Hopf algebras, where there has been a lot of Lie theory that's developed for this kind of objects. And these quantum analogs of contragradient Lie super algebras fit very naturally to this framework. They all arise as very special cases of this construction. Now, here is the answer to Anton's question. Angiono wrote a paper in Journal European Mathematical Society where he actually explicitly classified the quantum Serre relations for all these BFV. And there are lots of pages with different kinds of quantum Serre relations. There are more than 8 pages that are filled up with different kinds of quantum Serre relations in order to describe explicitly everything that's going on here. And there are so many pages because these are classifications not only of the super case, but also of these other examples that come from finite dimensional simple algebras in characteristic 2 and 3, and they have more and more complicated quantum Serre relations. But now we did not achieve exactly what we wanted. We have an intrinsic characterization of all small Lustig small quantum groups and their generalizations. So we don't have the big quantum groups of the Concini, Kac and Procesi. And to obtain those, Angiono did the following. He said, we will define a pre-Nichols algebra that is still going to be a Hopf algebra and everything else, but we're not going to quotient here by the maximal ideal that we quotient before. That was the one that was defining the Nichols algebra, but we will use the complicated Serre relations and the n powers of the non-Cartan generators. So these are like the odd roots in the super situation, and this is going to be the pre-Nichols algebra that we're going to be using instead of the Nichols algebra that was producing the small quantum group. And if we do that, now here is the dictionary that we're actually getting. If we take this pre-Nichols algebra semi-direct product with the group algebra and we look at the Drinfeld double, this is the generalization of the big quantum groups. We will call them large quantum groups now, not because they are larger than the big quantum groups, but we were just looking for an adjective that's going to distinguish them from the big quantum groups of the Concini, Kac and Procesi, which are just in the classical situation of simple Lie algebras. Of course, we're doubling the Cartan generators, the collection of Cartan generators, Ki, but that's completely fine. That's totally harmless, and it's being done in many other situations. If we don't double that, we just look at this semi-direct product, which in Hopf algebras people call bosonization. That is actually the quantum, the generalization of the large quantum Borel subalgebras. And if we're looking just at this pre-Nichols algebra itself, this is like the large quantum unipotent subalgebras. So all of these objects now have intrinsic characterization in terms of Hopf theoretic background. And the point is how we can actually use this Hopf theoretic background without doing concrete calculations with different super cases. Now, one thing that I want to say here is that, first of all, this braiding matrix, it is written like a Q, like this strange Q, but it is consisting its entries as some roots of unity. And in general, one thing that I'm hiding under the rock is that we're not only getting the big quantum groups of the Concini, Kac, Procesi, but we're getting also all of their multi-parameter versions, where we basically use different roots of unity on that braiding Qij. So even though that is written as a Q, that's a matrix whose entries are just roots of unity. And now the assumption, this extra assumption that we're placing is that this quantum matrix that consists of whose entries are roots of unity is actually obtained by specialization of some braiding matrix where we use an extra parameter nu. This is a free parameter that the entries of this one parameter matrix are these monomials in this parameter. And when we specialize nu to a root of unity, we're getting precisely the matrix Q that we start with. So this basically keeps pretty much all of Heckenberger's classification except throwing out some examples in low dimension. Those are not obtained by specialization. They're not treated by the theory that we developed. So we still have lots of extra examples compared to the super case, but still we're throwing out some low dimensional examples from the Heckenberger's classification. So what do we really get here? And the answer is we're getting all big quantum groups of the Concini, Kac, Procesi, and actually we're getting all multi-parameter versions of those. So we will be studying the Poisson geometry, not only of the DKP, but also of the multi-parameter versions, all big quantum supergroups. And there are two extra Hopf algebras that we're getting here. One is a quantum analog of a simple Lie algebra of dimension 34. It's in characteristic 2 that was first appeared in certain classification of Katz and Weisfeiler. So it was constructed by them. And also quantum analogs of a 10-dimensional simple Lie algebra in characteristic 3 that's due to Brown. So those two algebras have quantizations that are not sitting in characteristic 2 and 3. They're in characteristic 0, but the corresponding quantizing parameters are some very concrete roots of unity. They're not arbitrary roots of unity. And finally, to continue the dictionary, how do we want to think about these Hopf algebras in terms of generators and relations? So they have the usual generators E, F, K, and L, like in a quantum Katz-Moody group. The K Q-commutes with the E and F, and the L Q-commutes with the E and F. And when we commute the E and F, we get this expression, and the K and L's commute. So if it were possible to quotient by K equals to Li to Ki equals to Li. So in other words, to quotient by Ki minus Li by that ideal, we would be getting precisely something that looks like a quantum group, except that because of this multi-parameter nature, that's not always possible. So that's a minor detail. But now in terms of relations, we have these relations and some very complicated quantum Serre relations, and we will completely disregard those because we'll be basically handling those through Hopf algebra techniques. And the usual relations that must be there, these relations are also present without the quantum situation. So the n powers of some Chevalier generators would have to be 0, and also the ones that correspond to the non-Cartan simple roots. So now I have about 13 minutes to go through the results. So I want to say a few words about these results and about the methods. So first of all, because we had this assumption that the braiding matrix appears in a one-parameter family, the first part is trivial. The large quantum group is a specialization, so totally no rocket science. This is all trivial. That makes the large quantum group and the central subalgebra a Poisson order. Now we have a special central subalgebra that's generated by these n powers of Chevalier generators and root vectors. And the first point is that it is invariant under this generalized Lustig braid group action. It's not really a Weil groupoid, it's more like a braid group action. And the whole UQ is actually module finite over this Z epsilon. I'm tempted to say epsilon because this braiding matrix consists, its entries are just roots of unity. So this is all still very simple, but now the punchline is that the central subalgebra that is smooth is actually a Poisson subalgebra of the non-smooth full center of the big quantum group. And here is the first point where we will need something completely different because we don't want to check this case by case. And the upshot of that would be that the pair of the big quantum or large quantum group and this special central subalgebra that's smooth is a Poisson order. So the really difficult thing here is 3, where we don't want to do this case by case. So here is an overview of the strategy. If I look at the positive part of the ZQ, that's what's everything that's generated by the powers of E, we can actually describe this in an intrinsic fashion. It is the subalgebra of the full center of the positive part of the big quantum group that is invariant or fixed under a family of Skew derivations, which actually descend from the one-parameter quantum group, the one that has a Q in it. And then we prove a theorem that every time you do this kind of specialization and you consider something that fixed point subalgebra with respect to skew derivation, that is automatically a Poisson subalgebra. So that part that we're having in the third part here is almost automatic by a general theorem about fixed points of skew derivations.
Milen?
Yeah.
So could you say one word? What are those skew derivations? What are their generators, or what kind of skew derivations?
So those are precisely analogs of what people call the Lustig-Kashivara skew derivations of the positive part. So if you take a positive part that's generated by E and take an element there and commute it with a negative Chevalley generator Fi, you can write it down in terms of something that's in the positive part plus something else, and what is that stuff that's in the positive part is precisely this derivation.
Okay, so these are things generated on positive part by negative. Yeah,
like commutation with negative parts, precisely. Okay. Thank you. And then we still need to claim part 3, which is not about the subalgebra just generated in the positive part, but the whole central subalgebra. And here is where we use the invariance under the Lustig groupoid action. So if I have to prove that the Poisson bracket between different generators over here is still within ZQ, I can use the break group action to somehow move them in the positive part, modulo some trivial examples that cannot be moved simultaneously in the positive part, and check that the bracket there is within ZQ, which was already proved in step 1. So step 1 plus the invariance under the generalized groupoid action immediately produces this third part. So now we are done with creating our Poisson order, but that's not the end of the story, because we need to know explicitly what kind of Poisson algebra is ZQ. So it has to be the coordinate ring of some Poisson algebraic group. So I need to have like some Poisson-Lie group that is producing this ZQ, because ZQ is a Hopf algebra in addition to being a Poisson algebra. So there is definitely, the spectrum is definitely some Poisson-Lie group. What is that Poisson-Lie group? So here is exactly that stuff. So we produce these Poisson orders. One is for the large quantum groups, and the other is for the Borel picture. And these are Poisson-Hopf algebras, so their maximal spectra has to be some Poisson algebraic groups. What are they? And here is the second theorem. For each of these large quantum groups, the maximum spectrum of ZQ is actually a product of two Borel subalgebras, very similar to the classical situation. And the center of this Z greater or equal than 0 is just the Borel subalgebra. And what are these Borel subgroups? So first of all, they are opposite Borel subgroups of semi-simple algebraic group, of certain semi-simple algebraic group of adjoint type. So let me just say again, adjoint type means that it has trivial center, something like PSLN. And they're coming from the Cartan roots. For instance, if we're working just with the situation of quantum supergroups, which is somehow of highest interest, we're doing the following thing. We take the even part, we throw away any central things there. So we look at the derived subgroup there, and we take the corresponding group of adjoint type. So if you say you look like a copy of SLN and SLN, you just, so in other words, you have SLM times SLN, you just quotient by the center of that. And that is what is going to, the Borel subgroups of that is what are going to appear here. And finally, what are the corresponding Poisson structures? They are precisely the dual Poisson algebraic groups of this group GQ. But now this group GQ is no longer equipped with the so-called standard Poisson structure. It's equipped with those Poisson structures in the Belavin-Drinfeld classification that have trivial Belavin-Drinfeld triples, but still arbitrary continuous parameters. So these are precisely the Poisson algebraic groups that are behind these central subalgebras. And this is somehow the hardest part of the work, because here is where originally the Concini, Kac and Procesi did a lot of case-by-case considerations in order to prove the first part. Actually, also the second part, both of them are proved by case-by-case by reduction to rank 2 because of the 3 kinds of Serre relations. And what we do is we avoid any of that by the following somehow general strategy. So now in the world of all of these large quantum groups, when we do everything before the specialization, so we have a free Q parameter over there, we can look at 2 integral forms. So this will be integral forms over this algebra that's polynomials in Q localized at some polynomial of Q. So we invert some Q minus AI for a bunch of AIs. And now we have 2 kinds of integral forms. One is the non-restricted integral form that doesn't have divided powers, and the other is the restricted integral form that has divided powers. If we use the non-restricted integral form and we look at the corresponding specialization of the non-restricted integral form, this will produce precisely the negative part of the big quantum group. The restricted specialization before has never been used for Poisson geometric arguments. This is the divided powers, because somehow it doesn't really have anything to do with the specialization. But now the punchline is that if I look at this Poisson algebraic group MQ greater or equal than 0, that was the spectrum of this central subalgebra. And I want to know exactly what is its dual tangently by algebra. One can actually explicitly describe this dual tangently by algebra in terms of the specialization of this restricted integral form because of this perfect pairing. So the perfect pairing, if you wish, is a quantum analog of the pairing between Lie algebra and the corresponding dual Lie algebra when one of them is a Lie algebra. Now, this gives us a way to actually classify exactly what is that dual tangent Lie algebra, because we can describe it intrinsically in terms of the quantum group. And from there, we can get exactly what is that tangent Lie algebra. Now, let's look back at the spectra of these centers. So these are going to be some algebraic groups, but they're not completely arbitrary. We know that they're the spectra of these central subalgebras, and we know something about the coproducts of some generators. We don't know all coproducts, but some of them. Using those coproducts, we can say that those are Borel subgroups in semi-simple algebraic groups of adjoint type. So that completely tells us what should be MQ if we actually knew their Lie algebras. And now we can go back to this pairing and produce a Manin triple out of that pairing to explicitly describe what are the Lie algebras of MQ and MQ greater or equal than 0. And because we already know that these are Borel subgroups in this semi-simple algebraic groups of adjoint type, that completely describes both the Poisson structure and the groups. And now here is basically the upshot of everything. So if I look at this BQ plus times BQ minus, we can project it into the corresponding group GQ of adjoint type times some quotient of its maximal torus. And in the case of large quantum groups, the symplectic leaves of this are in bijection with some conjugacy quassis of GQ times points of this quotient of maximal torus under this projection. And then the corresponding algebras are isomorphic to each other across conjugacy quassis. If we were looking at the corresponding quantum Borels, then the spectra of the corresponding central subalgebras are actual Borels. They have canonical action by left multiplication by a torus, and in addition, they have symplectic leaves. So if I look at the torus orbits of symplectic cleaves, they happen to be again the double Brucha cells like we have before. But now this is all carried out in the super situation and also in the situation of these quantum groups that are quantizing the algebras in characteristic 2 and 3. And that's all that I had to say. So thank you so much for having me, and thank you so much for coming to the talk.
Well, thanks a lot, Milen. So thank you. Please, questions or comments? You can either unmute yourself or you can raise your electronic hand. Just in case, I have lots of questions, but maybe there are other people who want to ask. So let me then start, and then we'll see how it goes. So yeah, maybe let me, if you go back to the previous slide. Like one naive question that I have. So you're saying that all those algebras MQ mod M UQ mod M UQ, right? So they are isomorphic for each conjugacy class, right? But I mean, and what are they? Do we know something about what they actually are? Suppose okay, they're very good. They're isomorphic for different points, and so
yeah, so we're basically working on this right now. So we are looking at especially the type A. So because obviously the super type A at roots of unity would be possibly the most interesting if it appears in various kinds of physical theories. So we are looking at exactly what those algebras are. So we're putting more non-commutative algebra in the game. So we're basically proving that they're like Cayley-Hamilton algebras in the sense of Procesi, in the sense that they have traces and all that kind of stuff. But to be precise about the answer, what are they explicitly, we don't know yet.
Okay, and maybe somewhat related, like follow-up question. So you now have conjugacy classes in that group GQ, and then right. So this embedding of BQ plus times BQ minus, it's not surjective typically, right? I would imagine. So there are pieces of those conjugacy classes which are not covered. Is there some reasonable way to still assign so those limit points or whatever, those points outside the image, do you still have a natural way to assign to them those quotients, or it doesn't make sense, or what's the status?
So the status of one is that we have an additional part that says that every conjugacy class intersects the intersection of the image with any conjugacy class is a dense open subset of the conjugacy class. Yes. So we know for sure that every single conjugacy class appears. So we are talking about certain Zariski open subsets of the conjugacy classes. So we know that each of them is going to appear. What is the quantum group interpretation of those points that do not appear in this intersection? I have no idea. But definitely every conjugacy class is in the picture. There are no conjugacy classes at infinity that do not intersect the image.
Okay, but we don't know whether there is life outside the image.
That's right. We don't know what kind of non-commutative algebra corresponds to that.
Okay. More questions or comments? I warn you, if you don't ask questions, I have many other questions, but maybe the audience. Maybe let me continue with one more question. So you explained what happens with those quantum supergroups, which correspond to Lie, which are quantizations of Lie algebras where you have an even pairing. So what about the story of odd pairing, right? Of those gadgets which have an odd pairing.
Precisely. So somehow the point is that even pairing in the super world is precisely the same thing as contra-gradient. So in other words, they will all have presentations of this form. like a Kac-Moody algebra, except that this is not going to be Q raised to some single number Aij, but it's going to be multiple Qijs. So they all will have a Kac-Moody presentation. And that's the contragradient nature. The problem now with the others is that we can't really realize them within the world of this Yetter-Drinfeld, like over here. They cannot be realized as this kind of semi-direct products where we take group algebra of an abelian group. Possibly they can be realized in some other fashion in terms of this world, but in a similar world, but we don't have the developed Lie theory that could be used for that. So basically, our methods simply don't work for those because first we want this kind of realization in terms of Nichols algebras, and secondly, we want to have this Hackenberger's Lie theoretic framework developed there. So those are the missing ingredients that basically don't allow us to look at the others.
Okay. Thank you. So one more chance for other questions.
Can I ask one? So if I'm not mistaken, then the symplectic reflection algebra of Ettinghoff and Ginsburg can also be obtained via this formalism of Yetter-Drinfeld modules and Nichols algebras, blah, blah, blah. Then can you run the same game as you explained today for the symplectic reflection algebras? And if so, what is the result you get?
So a little bit of that what has been done in the work of Brown and Gordon. So they looked at those symplectic reflection algebras that have a big center. And they proved a theorem in that setting that you have a dense symplectic leaf and everything else is in codimension too. And they were able to actually use this to produce some representation theoretic results about symplectic reflection algebras. So that's a great comment. Yes, it has been done even before this Nichols business by Brown and Gordon. But the huge difference there compared to here is that there is an example of how it's called, like an almost symplectic manifold where you have a Poisson structure that has a dense symplectic leaf, which sort of never happens here. So the upshot of that is somehow representation theory behaves very differently in the two situations.
Okay, thank you.
Thank you for the question.
Thank you. More questions? So I think I have one final question. So how is it? There is this story of skein algebras, which also, I mean, it sounds very similar because they have a parameter q, and I think at roots of unity it's supposed to contain a Poisson subalgebra. So they have some kind of also Frobenius map. So it contains a Poisson subalgebra, which is isomorphic to some version of the Poisson algebra functions on modular flat connections. So how is it? Do you know, like, how parallel are those stories? Do you know how kind of your techniques would apply there, or what do you know anything about the relation about those theory of Poisson orders for quantum groups and the theory of skein algebras?
So they both fit into this picture. We have this picture for those of finite fibers, and on top we have this Poisson stuff that's going on there. In that world of skein algebras, typically we don't have any Nichols algebras in the background. One thing that we're basically working on, and so we will be posting a paper with Nguyen and Trampel possibly next month, completely unrelated to this, and that develops the theory of cluster algebras at roots of unity. We have a couple of papers on those. And this paper basically says that all cluster algebras at roots of unity have canonical Poisson order structures. And on the one hand, the skein algebras are concrete examples there. And on the other hand, if we look at this, if we look at cases 1, 2, and 3, where we look at the positive part and the non-negative part, those also have structures of quantum cluster algebras at roots of unity. So somehow, one thing that eventually will link both theories is that there are special cases of quantum cluster algebras at roots of unity. And that will be the thing that will be connecting skein algebras at roots of unity and big quantum groups at roots of unity. And somehow the first paper along those lines, that in the general framework of quantum cluster algebras at roots of unity, we have those Poisson order structures. We'll be just posting that in a month or so. But that's with these two different collaborators, Bach-Wen and Kurt-Trampel.
Okay, thanks a lot. I think.
And just one more thing that Antonio asked me, how about what are the Serre relations looking like? So this is the classical picture. So there are classical papers that classify Serre relations for Lie superalgebras. So for the first was a paper of Leites and Serganova, where they classified it in the A case. And then later, this is a paper of Rubin Zhang that describes explicitly the Serre relations in the classical situation, not the quantum, because the quantum is more complicated. It's not in any way inspiring to show those. But say if we're in the A type, where this is an even root and this is an even root, and this is an odd root that is that has length 0, then there is a Serre relation that looks like this, that evolves the generators around. It has the degree 4, and it's on 3 generators. So the typical thing for this super world is that you have lots of relations that involve more and more generators and higher powers. And this is somehow a simple snapshot of a typical kinds of Serre relations that appear in the super world. So I just wanted to show them how in general they look like. Yeah, okay. That's all.
So more questions or comments? If not, Milen, thanks again.
Thank you so much, Anton. Thank you.
Yes, thank you everybody for participation, and so see you next week at Global Poisson. Thank you.
Thank you again for having me over. Thank you.
Thank you.
Bye. Bye.